Modern software can now diagnose rare diseases, generate hyper-realistic film, and manage complex shipping lanes without a human in the loop. These tools arrived so quickly and effectively, they feel like a recent explosion of technological ingenuity. If current trends continue, by 2050, AI will be responsible for the predictive models that manage entire national power grids and the autonomous telemetry for deep space missions. We are watching a trajectory that replaces human intervention with machine optimization across nearly every industry. To prepare for that outcome, we have to look past the current marketing. The idea that these systems were recently invented in a Silicon Valley laboratory is a misunderstanding of computer science history. To see where the intelligence of 2050 is going, we must look at the exact moment the blueprint was drafted in the mid-20th century. We are living through the technical culmination of a scientific gamble that began 70 years ago. At the 1956 Dartmouth Conference, the founders of this field officially named it artificial intelligence. They were so confident in their logic that they believed a human-level mind could be coded and completed in a single summer. Their first strategy used rule-based systems. They attempted to build intelligence by writing a massive encyclopedic list of if-then commands that would tell a computer how to respond to every possible situation. This diagram shows the logic in practice. To help a computer identify a dog, the programmer had to define every physical characteristic. If it has 4 legs, and if it has a tail, and if it barks, identify it as a dog. This approach failed immediately because the real world is too messy for rigid lists. If a dog was obscured by shadows or missing a limb, the system had no rule to follow. It couldn't handle a single exception without a programmer manually writing a new line of code. Trying to hard-code human thought proved to be a dead end. Researchers realized that instead of giving the machine rules, they needed to build a system that could create its own. This shift led to a second proposal in the late 1950s. Rather than using rigid commands, researchers designed a system that mimicked the biological structure of the human brain. This was the birth of the neural network. This shows the architecture of that network. It consists of layers of digital nodes, or neurons, connected by pathways. When you feed data into the input layer, it ripples through the connections until it reaches an answer at the other end. The training process is based on trial and error. The machine makes a guess about the data, checks its accuracy, and then works backward to adjust the strength of its own internal connections. Over thousands of repetitions, the machine identifies which pathways lead to the correct result. It effectively rewrites itself, making the connections that lead to the right answer stronger and more efficient. By the end of the 1950s, the pioneers of the field had already established the complex mathematical framework that allows these networks to learn. They had successfully designed the architecture of a thinking machine, but they lacked the specific resources required to make it functional. The problem was one of scale. For a neural network to develop any level of accuracy, it needs to process millions of individual examples, and mid-century technology couldn't provide them. In the 1950s, data was stored on physical punch cards. To give a neural network the same amount of information contained in a single modern training set, you would have needed enough paper to fill a skyscraper. The hardware was another bottleneck. These mainframe computers were physically massive but mathematically slow. They couldn't perform the billions of simultaneous operations required to train even a basic model. This led to the AI winter, a decades-long period where the theory of machine learning continued to advance in research papers, while the actual technology waited for the physical world to catch up. That gap only closed when the internet provided a near-infinite source of digital training data, and microchips became small and powerful enough to process it. It took half a century for our physical infrastructure to reach the level of the 1950s blueprints. The large language models we use today are not a new invention. They are the original 1950s neural network designs, finally operating at the scale of the entire internet. Now that the scale has been achieved, the goal is artificial general intelligence. This refers to a machine that matches human performance across every cognitive category, from creative writing to scientific research. Most major AI laboratories are now working toward 2030 or 2050 as the technical window for achieving this level of performance. Reaching this point is the technical endpoint of the vision established at the Dartmouth Conference. However, as these machines become more capable, we face the alignment problem. This is the technical challenge of ensuring that an autonomous system's goals do not conflict with human safety or ethics. Between now and 2050, we will have to navigate the immediate consequences of this technology, including the systemic automation of middle-class jobs and the risk of bias being built into the algorithms that manage our society. The researchers of the 1950s provided the mathematical framework for a machine that learns, but they did not develop the safety protocols required to contain it. Artificial intelligence is a multi-generational project. The scientists of the past built the machine. Now, our generation must decide where it goes.